A civilization that's level 1 on this Kardashev scale has the power to harness the energy of its home planet. And that's extraordinary when you think about what that involves. On our home planet, there's the energy of volcanoes, of tornadoes, of hurricanes, and of earthquakes. Earth exhibiting a display of energy that typically we run from or die from.
So, why is the smartest path to planetary power not to tame tempests and volcanoes, but to manage sunlight? Because most of a planet's usable energy isn't in its occasional fury, it's in the steady river of starlight that bathes it every day. Earth intercepts about 174 petawatts from the sun. Humanity currently runs on roughly 20 terawatts. Geothermal heat flow is about 47 terawatts, tides a few more, and even the globe-spanning winds yield only tens of terawatts before you start changing the climate itself. A single hurricane does release enormous heat, but it's already disordered energy spread through warm vapor and turbulent air. The mechanically useful part is a tiny slice. You can't plug a wire into chaos. Covering just 1% of Earth with efficient solar arrays in sunny regions could yield a couple hundred terawatts, multiple Earth's worth of today's consumption. To climb another order of magnitude without paving vast areas, you'd likely turn to orbit. Collectors that tap near-continuous sunlight above the atmosphere, broken only by brief eclipse seasons instead of clouds and night. The first lesson is unromantic and decisive. Planetary power comes not from wrestling the planet, but from geometry, surface area, angles, and consistent flux. What do the laws of thermodynamics demand once you scale to planet-level watts? They demand respect for waste heat. All useful work ends as heat, and when you're talking tens of thousands of terawatts, that heat matters. Spread 10,000 terawatts across Earth's surface, and you add roughly 20 watts per square meter, comparable to or exceeding the radiative forcing that drives modern climate change. The planet would warm by several degrees, even if your energy were carbon-free. You can't negotiate with the Stefan Boltzmann law. The way out is not to wish away heat, but to relocate where it goes. Collecting energy in space and using it in space lets you radiate waste heat to space. Beaming power down to Earth adds heat here unless you countershade an equivalent amount of sunlight. There's a ledger, and it must balance. Harnessing planetary energy becomes less about finding new turbines and more about managing Earth's energy budget so that the biosphere's thermostat stays within its narrow operating range. If energy becomes abundant, what becomes scarce? Timing, control, and information. A planet-scale grid is a choreography problem. Sunlight cycles, seasons shift, weather varies, demand surges, storage technologies, chemical, thermal, gravitational, have physics-defined limits and trade-offs. High-voltage networks reduce losses but require continental agreements. Space-based solar promises baseload power, yet it introduces beam-pointing safety, orbital traffic, and debris dynamics. Microwave links must be precise enough to land on rectennas, not rain down on oceans or cities. Heat from data centers becomes an urban planning variable, and every intervention ripples into climate, ecology, and geopolitics. The hard part is not raw collection, it's correctly predicting feedbacks and keeping the system stable on a planet that is already a couple non-linear machine. Civilizations that ignore those feedbacks may simply overheat themselves into silence. That possibility reframes the Fermi question. It may be easier to light up a planet than to keep it lit without burning the stage you stand on. How does this change what progress looks like? It says the next rung is not a crown of thunder, but a reconfiguration of where we place matter and where we dump entropy. You build large orbital arrays and mirror shades that both collect energy and meter how much sunlight reaches Earth. You migrate the most energy-intensive industries, smelting, heavy computation, material synthesis, into cislunar space, radiating their waste heat into the black. You treat Earth as a sanctuary, reserving on-planet power for what must happen here. Food, water, shelter, culture. You drive computation toward physical limits, knowing that every bit erased has a minimum heat cost. You let algorithms schedule loads so that peaks flatten and temperatures stay within bounds. And you measure success not by boasting that you use all the energy of a planet, but by demonstrating that you can power billions of lives while keeping the climate steady and the skies dark enough for stars. In that light, advancement is clarity, recognizing that true planetary power is the informed placement of collectors, radiators, and responsibilities. When you align your technology with the simple accounting of physics, you don't just survive your own wattage. You earn the right to ask what comes next. Like if this was interesting, and hit the subscribe for more.